Okay, this week we are going to just see some simple applications of Newton's laws we talked here last week. Basically, we are going to talk about friction. Last week, we were not taking friction into account and all the people were like raising eyebrows. Now, finally, it's here. We'll talk about circular motion. And I think this is written like drag forces, but I think it's not included. But you can take a look at that too, if you want to. It's interesting. So the friction is something like this, right? If you have an object on like a surface, and if this object tries to move, these two things are in contact, and who knows what happens? Like microscopically, these things we can see are happening, but whatever is happening, there will be like a resistance to motion in the opposite direction to the motion. Okay, that's basically the friction. And the important thing here to note is like it's generally proportional to the normal force. So if you like draw the free body diagram, something like this, there is some force that moves the object. There is like the gravity pulling down, and there is the normal force acting on the object from the ground. And the friction force, we generally write it like, let me put F. Maybe I can write it for this time. Friction is equal to some constant. That's like that constant is some material specific constant we don't know. We can only measure it, or we can only observe it, or we have to extract it in one way or another. We can't just predict what it is. And the normal force. Okay. So, and since we are already thinking about like more moving parts, this is actually called kinetic friction coefficient. Okay. So I think there are a couple of things I need to like note here. First, this thing is not a vector equation. So these things are dependent on the magnitude. So the magnitude of the friction is proportional to the magnitude of the normal force. And the proportionality constant is called friction coefficient or kinetic friction coefficient. Yeah? So then like this means we need to determine the direction. Determine direction, because force is like a vector. We need to work with vectors. I had a question. Okay. And so since like the motion is always in the opposite direction, we say that the friction force is on the opposite, right? And finally, I just already said it, but like mu is like a material constant. It depends on the material, the moving object. It depends on the surface. It depends on the external conditions. It depends on, I don't know, pressure. It depends on all the like microscopic details of the environment. So, and of course, we can just look at some examples and then compare. And here is a table for this from your book. For example, the friction, okay, they just give you both the static friction and kinetic friction. And they have different materials, like for example, wood on wood is like 0.4 when it's static and 0.2 when it is kinetic. By the way, I think I didn't say it yet, but kinetic friction is when object is moving. And of course, that's not the only one. There's also like a friction force when the object is stationary, and we call it static friction. And this one is a little bit different. Let's write it like this, friction. So this is not an equality sign. This is less than or equal to, and exactly the same form, like static friction times F normal. Okay. So this means the maximum static friction you can attain is this one. And we understand this because as you like apply a force on an object, initially it doesn't move. And since the net force should be zero, up until this critical value, the friction force is equal to the net force applied. But when you reach this final value, you know it's going to move. And then that's why we are showing it with this less than or equal to sign. Okay. And then I think another note is like mu s is generally bigger than mu k. Actually, there's a third kind of friction coefficient, and this is called rolling friction. And when an object, like maybe I can draw something like that. So when this object rolls, you may think there's no friction, but actually there is, because there's still like some microscopic contact. There's some, who knows, some atomic things going on, but generally this is much smaller than all others, like smaller, actually much smaller than mu s and mu k. So we will generally neglect that. Most of the time, we will not talk about rolling friction. So here is like now I can come back to the table. Here's a table for some examples. So wood on wood, static friction coefficient is 0.4, kinetic friction coefficient is 0.2, the factor of 2. Ice on ice, it's like, look at the difference. Like when it's static, it's like 0.1. When it is like in motion, it's like 0.03. Like there is like almost like 10 times, what is it? Like almost like 5, 6 times difference. So metal on metal, if you have like a lubricated surface, there's a difference. Rubber on concrete, like you better have like a large one for this, because that's what we are using when we are driving. Rubber on other solid surfaces, 1 to 4. I think this is quite rough. This is about 1. Teflon, and your joints. Okay, you can see even your joints have like some friction, and you can measure these things. It seems like, right? Any questions?
Hocam,
Yes.
what is the maximum values of US or UK?
What is the maximum values of what?
UK, coefficient of static friction or coefficient of
Oh, I
kinetic
see. Yeah.
friction.
Generally, like I think generally it is 1, right? It can't be bigger than 1, but somehow I don't understand why they write it like this. Maybe it is like in some cases it can be like much larger than normal force, right? If you have, I don't know, if you engineer a kind of surface, like I don't know, like something like this, and your object just kind of like interlocks, something like that. Of course, this one will have like if, and this is like F normal, and the friction coefficient mu s or k times F normal is going to be bigger than F normal. I mean, it can be bigger than F normal, but under like generally it's between 0 and 1. Okay, it's like this thing, for example, they wrote like 1 to 4. I don't know how it can be bigger than 1, but I think there may be cases. Good question.
Actually,
Thank you.
I thought that the maximum value was 1, but in one previous exam midterm, one coefficient was something like 3 point something, and I just curious about that.
I mean, if they give you like, I think it can be bigger than 1, right? It's like, what does this mean? You have like a friction, and you are saying that it's like some proportionality times normal force. So the normal force is fixed. And let's say we are talking about static friction. So you can increase the normal force, but you can increase the friction force by keeping F normal fixed. And I think one way I just said was like this, right? You can just put these like wedges on the surface, and you can bring your block and put wedges on your block, and they are going to lock to each other. So this can be arbitrarily large, or you can think of like this. So you have like a surface like this, and your object can be something like that. So this top part is like, this is object. I mean, if, of course, these things are going to lock to each other, and you will not be able to move. I mean, basically, your like friction force is as big as the force applied. But I think this is a special case. Normally, we are not talking about these things. Normally, we are just talking about geometries like this. You put one object on like another arbitrary surface, and then I think it's generally less than one. Okay.
Yeah, thanks.
Good point though. Yes, I mean generally, if I find something bigger than one, I have to sit down and think what's going on, and I have to be careful, right? Right. So the second application is like circular motion. Okay, let's quickly talk about circular motion. This is like a motion, like let's say around a circle.
I have a question, Hojam.
Yes, yes.
Before you get into circular motion, for that's two bodies that are in contact on a flat surface. When a force is applied, so the applied force and the static friction, do they follow Newton's third law? That is, are they reaction and action based?
Yes, exactly. Very good point. Thank you. Newton's third law is like a law that nobody can break, right? Like exactly like you said, they obey the Newton's third law. If there's like for example, there's like a friction force. Actually, we had to like specify this, right? There is like a friction force. Let's call it friction on the block by the by surface. Let's call it, and there's exactly the same force on the surface. F friction on the surface by the block, and this is the minus of these guys. This is exactly like
that means
yes.
This is for this only applies for static friction, not for kinetic friction.
Yes.
Okay.
Yes, both of them, both static and friction.
Oh, okay.
And kinetic friction. They obey Newton's third law. Of course, we generally think of like the ground to be not moving, but I will show you an example that I will show an example where there's like a block and there's another block and there's like a friction, and the friction here, one acts on this block on that way to move it, the other one is acting on this block to slow it down. Exactly like you said. That's a good remark. Thank you. All right. So let's go with like a circular motion. Circular motion is a motion around a circle with constant speed. Okay. And to describe this, I think we can think of like a geometry. It's something like this. It's going with some around. So this is like a patch of the circle. And since this is like circular motion, this is like V1 and V2. They are, as you can see, like in the different directions, but their magnitude is the same. Okay. So I want to find. So what do I want to do? So I want to calculate the acceleration. Obviously, there is like a change in the direction of the velocity. So we need to find acceleration for this. Find acceleration. So how do I do that? I mean, the way I do this is like, okay, there's like a vector here, like this. And if I bring this vector here, I can look at the difference between these two vectors. and I can take the limit in which this angle goes to 0, and that's by definition the acceleration. So what I'm going to do is, like, maybe I can what can I do? I can draw a vector. Let me draw it like this here, and maybe I can, this is just a little bit, now push it back. Now I can, okay, this vector I draw. All right, now I know this is exactly the same vector. And now I need to study the geometry a little bit. So I know this, this angle is 90 degrees, right? And this angle is 90 degrees, right? And I know if this angle is, so delta theta, can extend it just a little bit. This part is also delta theta, because this should be pi over 2 minus delta theta. Okay, just a little bit geometry. Now I want to call this length delta L. I think I close it, but maybe I can delete this to show you what delta L is. So delta L is this amount of patch here. From geometry, you know, this is going to be delta L is equal to what? Maybe I ask you, what is delta L? How can I write delta L? So delta L, this little patch. And we are talking about this delta theta to be very small. It's like simply just radius times delta theta, right? So if delta theta is like 2 pi, I have the full circumference, but I have just a little bit, so this is like r times delta theta. And from that, for example, I can solve for delta theta is equal to delta L divided by radius. So this thing is the, let's call all the magnitudes of velocities. This is V, this is V. So this is a triangle with equal sides. And I know this is a triangle with equal sides too. And since this is delta theta and this is delta theta, these two triangles are identical. They're like scaled up versions of each other. So from this, I can write something like this. Okay, this delta V here. Okay, delta V is magnitude of V2 minus V1. And since these two triangles are equal, I can write it something like this, right? The radius, which is this radius, which corresponds to this here. This was R, this is V. And here I had R times delta theta here. Okay, this angle is delta theta too. This should be V times delta theta. Then delta V is equal to what it is supposed to be equal to. I just plug this in. Delta V is equal to V times delta L over R. Okay, good. And now let's calculate the limit, because that's what we care. Acceleration, by definition, is equal to limit as delta t goes to 0, v times delta L over R. So we said circular motion is a motion around circle with constant speed. The speed is constant. The radius is constant because it's around a circle. So I just take them out. I think Oh, okay. The limit delta. Okay, I need to write it this way. Forgot delta t. So this is limit delta v delta t as delta t goes to 0. And this should be, okay, there's like an overall delta t here. And I take the constant outside the limit. This is delta v over r. So limit delta L over delta t as delta t goes to 0. Now I ask you, what is this quantity? Anybody? What is length divided by time? Velocity, right? Exactly. Radial velocity is basically v. So then the acceleration happens to be v squared over r. Okay. So we basically derive something you all know from high school. So, okay, what's happening here? Let's write it here. So here is the circle of the motion. You know, constant speed. Speed is constant at any point. So you have like some v here, like some other v here, something like that. V. But as you can see, the direction is changing. And what we found is the magnitude of acceleration is also constant, but it's always inside like this, right? And its magnitude, okay, A is the magnitude of acceleration is square of velocity divided by radius. It's a really nice formula that we'll use a lot. All right. Any questions? Any comments for this? I guess everybody already knew that, right? So let me just define a couple of things related to the circular motion. One thing is like frequency. Frequency, by definition, is like number of revolutions per second. Okay. And its unit is, maybe I ask you, unit of frequency is number per second. Number is unitless. Number of revolutions doesn't have any unit. So it should be 1 over second. Sometimes people call this hertz. And the period, you show it, okay, frequency with F, period with T is the time for one full revolution. Okay, and its unit is, of course, this is the unit of time, second. And velocity, let's write this, v, or maybe speed, which is constant, is of course delta x or delta t. Delta x, we can take the full circle, it's like 2 pi r, and delta t is the period. Or you can write it in terms of frequency, it's like 2 pi r times f, okay? We just didn't do anything. I just introduced f, t, and I calculated v in terms of radius and f, or radius and t. So here's the exercise from your book. It says like, can the kinematic equations for constant acceleration be used for uniform circular motion? It's saying that, okay, the acceleration is constant. Can we use constant acceleration equations we derived earlier last week? What do you think?
I think no, because the direction changes.
Exactly. Thank you. So this is like acceleration is constant. It doesn't mean the acceleration is constant, right? It means the magnitude of acceleration is constant, but its direction is changing. So we cannot use equations like this. So be careful, and like these are like for just not only the magnitude but also the direction should be constant for you to be able to use this. So for circular motion, unfortunately, we can use this. And there is another exercise. The moon's nearly circular orbit around the Earth has a radius about this, in a period of 27 days. Determine the acceleration of the moon toward the Earth. Okay, maybe I can quickly go through this. So A is equal to, just try V square over R. We need to determine V, and I already wrote an expression for V. V is equal to 2 pi times R divided by T. Then, okay, you basically have 2 pi, you have radius, you have time, 27 days. You find V and you plug it in here, and then you find acceleration. All right. Any questions? Simple stuff, right? Hopefully. So, okay, since in this circular motion, there is acceleration, and we know from Newton's second law, if there is acceleration, there must be force, right? Because was written, so Newton's second law says something like that: total force was equal to m times a. In the circular motion, there is a, then there must be a force. And we can basically use Newton's law. Force is equal to m times a. We just found a to be v squared over r, so force is equal to m v squared over r. And we call this centripetal force. Okay. Sometimes people like think of this circular motion to be like some center fleeing force, like a bad high school habit. There's no force outside the circle, right? If you are like in a circular motion, and you may feel like there's like some force pulling you out, that's only your illusion. There's no such force. There's only one force, and that force is the force that pulls you to the center. And that's your centripetal force, okay? Do not, okay, if you, I think most people don't have this habit, but if you have the habit of writing forces like this, forget about that. Try to fix that bad habit, because it's wrong. So maybe I can just put a cross here. No such force. No such force in circular motion. So, okay, let's do an example and then see how this works. So here's the problem from your book. A conical pendulum, a small ball of mass m suspended by a cord of length L, revolves in a circle of radius this, where theta is the angle the string makes with the vertical. Okay, let's write this. So this angle is theta. In what direction is the acceleration of the ball, and what causes the acceleration? Okay. Let's draw maybe a free body diagram and see. I would start with some G, and there's some tension T, and that's all I need, right? So this tension has like two components. Tx. So if that angle is theta, this angle is also theta, and Tx should be T cosine theta. So if that's the center of the circle, other component of T is towards the center of the circle, and that's equal to, let's call this T. Okay, I think I don't know why I call this Tx. Maybe I can call it Ty. Tx, this is equal to T times sine theta. And now I know, okay, this ball is not moving along this direction. So it's on a perfect circle that's at a level. So in the case, so because the force is towards the center, because the acceleration is in the same direction. Was it normal force in this? It is because force is towards the center, because the acceleration is in the same. Exactly, yes, yeah. So force is towards the center and acceleration is in the same direction with the force. That's correct. In the case of an object on a string that's swung in circular motion, is okay to say that the force the object exerts on the string can be termed as centrifugal force. I think we don't call centrifugal force, we call it centripetal force. And with the centrifugal force, if you mean something like this, I think try not to use that jargon anymore. It's actually not like a terminology. It's actually like I think it's like a physical misconception, right? When people draw forces like this, that's wrong. That's physically wrong. It's not some misconception, or like it's not like a language. It's not terminology. It's like physically incorrect. Because if there's such a force, there must be a result of this force. And in the circular motion, there's no such thing. All right, let me just set up the equations. So there's no motion along this direction. So I'll write total force along y, it should be 0. Then Ty, which is T times cosine theta, should be equal to m times g. Okay, total force, I'll say x, but maybe I should have called it radial direction, but let's call it x, is equal to T times sine theta, and that's equal to, okay, what are we trying to do? In what direction? Oh, and what causes the acceleration? Okay, it's like m times a, and from here we can find an equation for a. A is equal to T sine theta over m, which turns out to be g sine. Okay, I think I forgot something. This is t sine theta, this is t cosine theta. So this t is from here mg divided by cosine theta. Let's plug this in the other one. Mg over cosine theta times sine theta over m. So these m's cancel. I have g times tangent theta. So in that direction is the acceleration. The acceleration is always radially in towards the center of the circle I draw. And what causes this acceleration? The reason for this acceleration is the tension. If you didn't have the tension, you wouldn't have that acceleration. So this is A. And B, calculate the speed and period, time required for one revolution of the ball in terms of L, theta, G, and M. Okay. B, we already calculated A to be G tangent theta. And we know from the above, it's like V squared over R. Then V is equal to R G tangent theta root. Okay, something like that. So we calculated the speed and the period. So v is equal to 2 pi r total length divided by total time, which is t. And we are trying to solve this for t. T is equal to 2 pi r divided by v, and this should be equal to 2 pi r divided by r g tangent theta. I think I can combine these two factors, like 2 pi, what is it? 1 over, okay, maybe it's like root r over g tangent theta. Hopefully I didn't mess up the angles, but I think it's something like that. Okay.
Hocam,
Yes.
how we get the tangent theta?
So what I did is like something like this. I set up the equation for this direction. I said the total force along this direction should be 0. So Ty, which is equal to T cosine theta, should be equal to mg. T cosine theta is equal to mg. And I solved this for T, which gave me mg divided by cosine. Later, I looked at this direction and I said total force, which is like T times sine theta towards the center of the circle, should be equal to m times a. And I solved this for a. It's equal to a is equal to T sine theta divided by m. That's what I wrote here. And I plug this T in here. So this T is mg over cosine theta, and I multiply it with like sine theta over m. So the m's nicely cancelled. What I ended up with is g times tangent theta.
Okay, thank you hocam.
You're welcome. Any other questions? Should we continue? All right, let's see another application of this circular motion, and it's actually on the highways. So when you are like in a highway or in a road, and when you're turning with like a sharp, when you are making a sharp turn, you probably felt the circular like force, right? That fake force that I told you about. This is actually like perfectly defined circular motion that like obeys the kind of acceleration we just found. And let's write that down. So, okay, here, I think I have the geometry here. Basically what happens is like, that's your car. It has a weight that's pulled down by earth with some mg, and there's like some normal force. And when you're turning, you're supposed to execute this circular motion. There has to be like some force towards the center, and that force is actually coming from the friction. Okay. And the friction in this case, I think the geometry of the problem goes something like that. Friction is equal to some mu, the general static friction, because there is no, we are assuming there is no sliding on that direction, is equal to normal, which is equal to mu s times mg, and this thing should be equal to m v squared over r. Whatever v is, whatever the radius. So basically, if you know your speed, if you know the radius of the curve here, and you know the mass, you know this exact motion. That's how we describe this. Maybe I can like show you an example to see how this works. Here's example 14. A 1,000-kilogram car, okay, just put this on the side, runs a curve on a flat road. So we start with this flat road here of radius 50 meter at speed of 15 meter per second. So the question is, will the car follow the curve or will it skid? Okay. So the, okay, force, okay, I think maybe I can write it like force of circular motion should be less than or equal to force of friction. If this happens, there is no skilling, no skilling. Okay. And this force of circular motion is mv squared over r should be less than or equal to, and the friction force is exactly what we wrote, mu s times mg, m's cancel. So, okay, v squared over r is what? It's 15 squared divided by r is 50. We are trying to find if this is less than or equal to mu s times g. Mu s is 0.6 times g is 9.8. I think on this side, similarly, I found 4.5. On this side, I found 5.6. So this actually checks, so there's no skilling. Okay. So this is A. And B says if the payment is IC and mu s is 0.25. B, if mu s is 0.25, you basically have exactly the same thing. 4.5. Is it question mark less than or equal to mu s times 9.8? But mu s is now half of what it used to be. So this is something like, I think I found 2.45. So that doesn't satisfy, so there will be skilling. Right? Right? So another thing is like, okay, since friction is kind of uncertain, people sometimes engineer this angle on the highways, and that is called banking. When you bank the highway like this, or like maybe you saw these like in the car races, they have like perfectly banked roads so that the cars do not slide and just get out of the road. And for this, you need to like do the free body diagram like this. So there's like force down, and since there's like an angle with the vertical direction, normal force is along this direction. And you can kind of see this normal force has a component along this line. So, okay, this is the normal force, and it has a component along this x direction. And this force definitely will like cause like circular motion like this, and you will not even need friction in that case. Of course, if you have friction, it only helps, but even without friction, you will be able to execute this circular motion due to this angle. Okay, and that's kind of useful. And I think I'm going to show you an example with this. Maybe I can look at this example for now. For a car traveling with speed v around the curve of radius r, determine the formula for the angle at which the road should be banked so that no friction is required. And B, what is the angle for an expressway off-ramp curve of radius 50 meter, the design speed of, like, I think I'm going to solve a problem like this, but I think this is just the maybe advertisement of what's coming. Right? Any questions? Any comments?
Hocam, in the previous example, don't we need the kinetic friction coefficient? The question gives us the static one.
Yes. In this case, okay, there are like two kinds of motion, right? If you were to study motion along this direction, you actually need actually you need actually a rolling friction, right? Because your tires are rolling. And if you are studying motion along the orthogonal direction, like this direction, we assume that there is no motion, there is no skidding. If the car was skidding on this direction or this direction a little bit, you are absolutely right. We had to use the kinetic friction because there was motion. But we are assuming it's like perfectly stationary along that direction. And this is only possible if you are going through like a perfect circle. Is that clear? So if this car was skidding like this, you had to use the kinetic friction coefficient. But we are saying that along this direction, there is no motion. It's completely like stationary along this direction. That's why we are using the static friction. Does this make sense?
I got it. Okay, thank you.
Good, good. Thanks for the question. That's a good point. Well, so far I've been talking about like uniform circular motion. Now let's talk about something called non-uniform circular motion. So in this case, okay, the object is still, this is still following a perfect circle. But its speed is not constant. Okay, this is the definition of non-uniform circular motion. Right? And the way we do this is that we just basically decompose the force and study it component by component. So, okay, what we'll do is like decompose motion into, what do we say, like into radial and tangential components. Okay. So what this means is like you have, okay, you are still following this perfect circle like this, but you have now not constant speed. So this V here is different from this V, maybe it's increasing like this, maybe like that, okay? You're speeding up on a circle. Then there must be a force towards the center, which keeps you along this circle, but there must also be a force tangential to the circle. Otherwise, this vector, the acceleration vector here and here would be exactly the same. If there's an increase on that direction, there must be a force on that direction. And another direction here, and another direction here, okay? It basically like study these each component separately. And we can talk about exactly like Newton's law for these decomposed coordinates, like tangential acceleration and radial acceleration. And okay, a tangential, I'm writing the magnitude of tangential acceleration is the amount of change in the speed, dv dt. Pay attention that like I didn't write vectors. Basically, if your velocity is like 5 here and if your velocity is like 10 here, you just basically take 10 minus 5 divided by time. Right? And a radial, since this is still a perfect circular motion, although non-uniform, radial acceleration is still v squared over r. And so to find the vectors, you just do this. Vector, full vector A, entire acceleration is equal to A tangential the magnitude along tangential direction times, maybe I can not confuse you, maybe I can just put a vector to indicate that I'm talking about this direction. Okay. And a vector A radial, and I'm talking about this direction. Right? Maybe I can just go through this example, which kind of explains what's going on. So a race car starts from rest in the pit area and accelerates at a uniform rate to a speed of 35 meters per second in 11 seconds, moving on a circle track of a radius 500 meters. Assuming constant tangential acceleration, find the tangential acceleration and B radial acceleration at the instant when the speed is 15 meters per second. Okay, let's just use these equations I already wrote. So A tangential is equal to what should be equal to. So we are assuming it's like a constant tangential acceleration. That means the increase in speed, maybe I can write it like this: delta V tangential divided by delta T. And the problem says it reaches to a speed of 35 meters per second. Okay, delta V is 35 minus, it starts from rest, 0, divided by, and total time is 11 seconds. And from these numbers I found, okay, 25 divided by 11, I found something like 3.2 meter per second square. Right? This is A. And B, radial acceleration. Okay, we already wrote it, a radial. So we are like, radial acceleration depends on time now, and they are asking us radial acceleration at the instant when the speed is 15 meters per second. When the speed is 15 meters per second, we know the radial acceleration is going to be E squared over R, and this is equal to 15 squared. Okay, maybe I need to write units just to keep it brief. Over radius is what? 500. And from here I found something like, okay, 15 times 15 divided by 500 is 0.45 meter per second square. Okay, simple stuff, right? Part B, can you explain? Yes. So the like problem is something like this, right? You start from rest and you speed up. Like you speed up, as you speed up, your tangential velocity increases. Like your speed here is 0, your speed is bigger, 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 and bigger. And the problem says, what is the radial acceleration at the instant? So at any instant, wherever you are, there's like a radial acceleration, and that radial acceleration should be the acceleration from circular motion. Otherwise, you wouldn't be following the perfect circular route. And that's what I used here. So radial acceleration at any instant is equal to V squared, the speed at that instant, divided by radius of that circle. This V itself is not constant. That means radial acceleration, the magnitude is not constant. And I just basically plugged in this speed. Speed is 35 meters and radius is 500, and 35 squared divided by 500. Oh, I think I messed up. This V should be 35. 35. Let me recalculate this. Here,
Sir, it should be 15.
okay, 35.
I think 15 was correct. The book did it that way.
Oh, yes, it's asking the 15. Yes, sorry, yes. I mix up. So this says 35, but it's actually, the question is asking the moment when it was 15. Yes, thank you. So let me take this back. And then I multiply these numbers, I found this, right? Is that clear? I mean, the problem already gave you like V and R. I just take the square of V and divide it with R to find this instantaneous radial acceleration. Good. Any other questions? I think that's all for today. Maybe I can go with one example and see how far we can go. So a 4 kilogram block is set on top of a 12 kilogram block, which is accelerating along a horizontal table at a is equal to 5.2 meter per second square, like in this figure. But mu k is equal to mu s is equal to mu. So the problem is saying that let's take this as an approximation. They are not equal, but the problem says take it, so we'll do this. So A, what's minimum coefficient of friction mu between the two blocks will prevent the 4 kilogram block from sliding off. So the problem is what friction should we have here so that this block on top does not just slide and fall off. Maybe I can talk about like a free body diagram of this block. So for not sliding, or not having sliding, the acceleration of, okay, let's call this, I don't know, let's label these, let's call this block A, and then let's call this block B. So it's easy to refer to them. So acceleration of block A, and let's call this table T, which is fixed anyways, with respect to table, should be equal to 5.2 meter per second square, which is equal to acceleration of block B with respect to T. If I get this condition, there will be no sliding. Any objections? And it seems like the only force on block A is the friction. So we can, okay, maybe I can draw the free body diagram. Here there's some friction. There's like this guy, MA times G. And there's this normal force. Maybe I can put all the way here. This is this is F normal. And the friction force should be acting on this way so that block moves, right? This is F friction. Now let's write this F. Maybe I can write it like a force on A by B. So this is due to friction. Okay. Should be equal to, of course, it's equal to mu times normal force, which is mg, but this should also be equal to, okay, m is which m? Let's specify, let's move just a little bit. This is m a. This should be equal to m a times a of a with respect to the table. Good. From this, we already find mu. Maybe mu minimum, because it can be bigger than that, and that's perfectly fine. Minimum value should be, okay, cancel these a's. The acceleration of block A with respect to table divided by the gravity, and this is like 5.2 meter per second squared divided by 9.8, and this is something like, what did I find? I found 5 divided by 0.53. 0.53. Okay, is that clear? Any objections? Any questions? So the friction equals applied force for block. Exactly, yes. So the only thing that can apply force, as the figure is not showing, is the friction. There is no other force. And we are saying that they are moving together. There should be no sliding. Then this friction should be keeping these two guys together. And that condition gave me this friction coefficient. Now B says if mu is only half this minimum value, what is the acceleration of 4.0 kilogram block with respect to the table? Okay. Like we are saying, mu is half of this value, which is 53. It's equal to what? Let's call it 26. And now our task is to find acceleration of the 4 kilogram block with respect to table. Okay. So the force now on A by B is equal to this new mu. Maybe I can call it mu prime to indicate that's like a new one. So this is mu prime times MA times G. And you know that's the only force along that direction. There's no other force. And by Newton's law, this should be MA times A with respect to table. And let's call this A prime to tell that this is different. That's the new situation. Okay. Is that okay? Any objections? And from here, just cancel A of A with respect to table in the new case is equal to mu prime G divided by, oh, that's it, mu times G divided by nothing. And if you multiply, it is like 0.26 times 9.8, and I found what? I found 2.6 meter per second squared. So because the problem says like this, because the problem says if mu is only half this minimum value, right? And we found the minimum value to be 53. Half of 53, I took approximately 0.26. Is that clear? Does this make sense? So here's a problem, it says if mu is only half this minimum value, and this is the minimum value, and I just halved it. Anybody with any objections to this?
Without doing that, if the mu is half, the acceleration will half, you can say.
Let me think.
Because
Acceleration is, yeah,
only
it seems like,
that moves
yeah.
to A is mu.
Yes, I think you can say that for this case. I think you are correct because it seems to be working, right? This is 2.6 and it used to be like 5.2, so it's like half. That's correct. All right, then C, okay, if mu is on blah, blah, okay. C with respect to 12.0 kilogram block. Okay, I think it's like AB. Maybe I can write C, acceleration of A with respect to B, that's what they're asking. That should be equal to what? A of A minus A of B. This is 2.6 meter per second square minus 5.2 meter per second square. It's basically equal to minus 2.6 meter per second square. And it basically says if you are like if these are cars and you are moving with this car, and if you look at this car, it'll look as if it's moving with an acceleration of minus 2.6. That means acceleration in the opposite direction. Okay? Simple stuff. And what is the force that must be applied to 12 kilogram block in A and in B, assuming that the table is frictionless? Okay, now this is the part that it gets interesting. A, B, C, D. So, okay, now we need to draw the free body diagram of the B. Like, let's write it like this here. I'm going to draw it just a little bit small. Okay, there must be a force applied on this guy to move the whole thing. And there's no friction here. So I'm not going to take this into account. But the friction on here, exactly like what we talked in the first hour for that question, right? If there's like a friction on this guy, are they the Newton's third law pair? Yes, they are the Newton's third law pair. And the force here is on the opposite direction. Maybe I can call this force on B by A. This is also due to friction. Okay. So FBA and AB are Newton's third law pairs. Because it's in the opposite direction with respect to B. That's why it's minus. Right? And now total force is F minus the friction force, which is mu times, this is MA times G, should be equal to MB times A. And this should be acceleration of B with respect to table. And this force is equal to B times A BT plus mu and A times G. Is that clear?
Hocam, may I ask a question, please?
Yes, go ahead.
Hocam, in which direction does the A move in part C?
In
Right.
both cases, it moves in that direction. But in part B, it moves just a little bit slower than this guy. This guy is much faster than this guy. That's why the acceleration of A with respect to B is negative in part C.
Okay, thanks.
Of course, they both move in this direction, but this is much faster.
Hocam,
Yes,
where is the table friction in D?
there is no table friction, right? It says here, it says assuming that the table is frictionless.
But it says in B. I know. Am I wrong?
So now in both of them, table is frictionless, but the difference between A and B is in one case the friction coefficient is 53. In the other case, the friction coefficient is half
okay,
of
okay.
that, which
Okay,
is
thank you.
0.6.
I understand now.
Yeah, this is a little bit like not a good statement, right? I think it kind of like sounds like maybe should I take the friction, right? That's a good point. So that's all. Maybe I can like put these numbers and calculate. Yes.
Maybe we can calculate it shortly by take the A and B 1 unit because they are moving together.
Exactly. Yes. Yes. You can do that absolutely. In part A, you can definitely do that. In part A, they move together, and we definitely can do that. But in part B, we cannot do that, right? Because
Yes,
in part B, they are different. But I think let's just put these numbers in. So maybe what do I write? If what for mu is equal to 50.53, force is okay. I know MB, I know MAB with respect to table. I know mu, I know this, I know this. I just plug these numbers, and what I found here is, let me just write the results. I found minus A and 5. First one is 20.8 Newton. So plus 62. I found something like 83 Newton. And for mu is equal to 0.26. I found F is equal to 72 point. Okay, forget about points. It's about 70 Newton. Okay, I think this last part is not a valid statement, but I think we know what they mean, right? What they mean is calculated for mu is equal to 0.53 and calculated for mu is equal to 0.26. And the equation is the same equation. F is this equation, and B is known, A is known, mu is either 0.53 or 26, MA and G. Everything else is known. Good. Any questions? Any concerns? I think we have time for one more question, maybe. So if a curve with radius of 85 meters is properly banked for a car traveling at 65 kilometers per hour, what must be the coefficient of static friction for a car not to skid when traveling at 95 kilometers per hour? All right. So that's the problem I told you earlier. So let's try to solve this. Okay, for like just like keeping it a little bit like a more concise, let's call this. This is the design speed. V design, or maybe I call it V1 just for cold, just for short. And let's call the other speed this one V2. So the difference is this is what you should be traveling. That's the recommended speed. But of course, some people are like reckless drivers. They can speed up and they can drive at this speed. And in this case, they are relying on the friction. They may say, "Oh, it's like friction, blah blah," but you know, it's not a good thing. But let's calculate. So I need to write the free body diagram, which is already given here. There is gravity pulling it down, mg, and the normal force, as the name suggests, is normal, so it's always perpendicular to the surface like this. And it has two components. One is along this direction, let's call this x, f of x, and the other one is in the perpendicular direction. And the nice thing about this is that x direction is the direction of the circle. So if you draw a perfect circle, and if this dot is your car, and this direction is just the center. Okay, I didn't draw it nicely, but you get the idea. Maybe something like here. So that's the car. That's the direction x, which has a of r. Okay. Now we can set it up. So from the vertical direction, there should be no motion. So f normal times, okay, let me take a look. This is f normal. I projected this guy. So this guy should be equal to this guy so that this guy doesn't move along that direction. So f normal times cosine theta should be equal to mg. Okay. Then I can solve this for normal. F normal should be equal to mg divided by cosine theta. Okay. Now the direction along x direction is f normal times sine theta should be equal to the centripetal force, which is v squared over r, and this v is recommended speed. Maybe I can write it a little bit more visible. This one is v1 squared over r. Okay. So like we said, if you drive with v1, you don't need any friction. So we are not taking friction into account for this part. Hopefully that's clear. And what is unknown here? The only unknown here is, okay, we don't know f normal and we don't know theta, but we related f normal to theta here. So let's plug this in here and find an equation for theta. So if we do that, g sine theta divided by cosine theta is tangent theta. And that should be equal to m, this design speed, v1 squared divided by r. Cancel m. And this gives me an angle for theta. Theta is inverse tangent v1 squared divided by g times r. Good. So there's mg and there's normal. And I project this f normal along this vertical direction, right? F normal times cosine theta is this vertical direction. This is fn times cosine theta. That's what I wrote here, fn times cosine theta. And only if this is equal to mg, this is in equilibrium along this direction, right? Otherwise, it would be going up or down. So the net force along this vertical line should be 0. That's why I have this one. Now, this normal force has two components. This one, a component like this, which is towards the center of this circle, and a component along this. So I already found this component from this vertical equation. And now for this component, I just write Fn times sine theta, which is this angle, is equal to mv square over r. And right now there is no friction. Now I will put the friction in a moment if this procedure is clear. If everybody is fine with these equations, we will proceed to find friction and we will see what it should be for a driver of faster speed. Is that clear? Should we convert kilometer? So yes, at the end, but I still didn't use numbers, right? I'm just using V1 for now. So at the end, I'm going to find something in terms of V1 and V2, and we will convert them and put it in the equation. But for now, let's keep it general, because I don't want to write these numbers here and there over and over again. Any objections? Now let's put the friction, and the friction is like what? Friction is going to be, okay, maybe I can use a different color to make it more visible. So friction is going to be on the car, and it's going to be along this direction. This is F friction, okay? Any objections to that? Now, as you can see, this friction also has two components, right? It has a component along the circular motion, like this, radial circular motion acceleration, and it also has a component along this direction. So I have to write them one by one. So let's write it. So the first one, okay, let's pick a different color. So F normal times cosine theta should be equal to, okay, first, of course, mg, and I need to also take the projection of this guy to here, right? Because I also have this one now. Then it is going to be equal to plus this mu that we are looking for times F normal times its projection, which is, okay, if this theta is this angle theta, this is 90 minus theta, and cosine 90 minus theta is sine of theta. This is equation number one. And the other equation is F normal times sine theta. This is going to be, okay, F normal times sine theta. This is the projection along the radial direction. And I need to add the friction force plus mu times F normal times, okay, this one is, I think, cosine theta. And this one should be equal to m. Now I'm using this second speed, V2 squared over R, right? If you are going with this V2, you need the friction, and we put it in this form. All right. Any objections to this? Now, like exactly like we did in the previous part, I can solve this for F normal. The first one, for example, F normal cosine theta minus mu sine theta should be equal to mg. Put this here, and from that, I find F normal to be equal to mg divided by cosine theta minus mu sine theta. Now I'm going to put this in the other equation. The other equation is F normal times, okay, F normal times sine theta plus mu cosine theta. But I know what F normal is, so let's write it. So let's copy this. And Maybe I can put it here, paste. This is f normal times this. And now I can delete this and take it back. Should be equal to, this should be equal to m v2 squared over r. Now you can see in this equation, the only unknown is this mu, because we already found theta from here. So let's do this. Let's cancel these guys. Oops. Cancel m. Oops. Cancel m with this m. Okay, let me take a look what else I can do. From this, I take it to the other side and I say, okay, sine theta plus mu cosine theta is equal to v2 squared over gr cosine theta minus mu v2 squared over gr sine theta. And now I collect mu on one side, mu, this is cosine theta, plus v2 squared over gr sine theta should be equal to v2 squared over gr minus sine theta. And if I divide this with this guy, I have mu. Okay, and I have more like this. And that's the end of the problem.
Hocam,
So-
may I ask, pardon,
Yes, go ahead.
can I annotate?
Yes, go ahead, please.
There is a frictional force, and friction force has y vector, so mg plus y vector of frictional force equal to fn cos theta. So I think we found the theta wrong in the
Okay, so-
beginning of the
So
question.
for this part, I neglected the friction, right?
Yes.
So there is no friction on this part. You think that's wrong?
Yes. I think that way.
Yeah. I think the idea is, so when these people design, like properly banking means when they design, they don't think about friction, right? They think about
We don't need
problem.
friction.
Exactly. In part A, we are saying that, okay, this road is designed for this angle. That means this is designed for this velocity. And that means your angle determines your velocity, v1. That's why I try to first spell it out in this form. So the angle perfectly determines the speed, or speed perfectly determines the angle, and there's no friction here.
It's always
You don't
clear
need
now.
exactly. You don't need friction here. And now, of course, people don't drive with the rules, right? People will drive with higher speed. There are like all kinds of reckless drivers, and the question is, how come they can just go through this road without sliding? And for that, we need to take the friction into account. And when you put the friction into account, you have two equations like this. And the angle is already found from this design speed. I put the design speed to find the angle. And when I solve it for mu, that's what I find for mu. So what this says is, if mu matches this V2, this guy is going to be fine. But if mu is less than this guy is going to slide. All right?